Okay, so with Braden and the video game rental one, we were just hammering out the fundamentals of the budget constraint. And I think the last thing I left you with was, and let me just go back more generically to, I guess we'll go with good old beer and pizza here or something. So quantity of beer, quantity of pizza. And the budget constraint is defined by what variables? What was this thing that we called the budget constraint that looked like this? The budget line or budget constraint. What was it dependent upon? Prices of the goods and income. Okay. Now there was two other variables, the Q's, but what are those to the problem? Quantities that are ultimately purchased. So those are the choice variables in the optimization process, right? We're going to choose a quantity of pizza and beer subject to having a certain amount of income and the price of beer and the price of pizza. So these are the exogenous variables, the external things that determine what our endogenous variable, endogenous means our choice variables, the things we're choosing. These are the external factors that we're facing. That sets up the optimization problem. All right, so the piece of the puzzle that we haven't got to that we're going to get to today is bringing in the utility function into the whole process of how do we maximize utility subject to a budget constraint. And as we looked at indifference curves before, we talked about it being the samurai sword of the three-dimensional utility function that starts at the bottom, and if we're measuring the beer axis there and the pizza axis there, and we're measuring utility getting larger as we go along this corner, and if we imagine that three-dimensional utility function, it comes up and over us like a big cave, a big cape, and if we freeze utility at a certain level, like right at this line at 100, and we cut through that three-dimensional surface, and we drop it straight down to the two-dimensional space of the beer and pizza space, we get indifference curves. And those indifference curves then, at each slice, as we go higher and higher up, each person, and these shapes don't have to be parallel, they could maneuver around, they could flatten out as we start to get up higher maybe, who knows. It's all determined by a human being and their preferences. And so each one of those slices is moving further up the utility axis and taking another slice and dropping it straight down. And so this is sometimes referred to as our indifference map. It's important to remember that there's an infinite number of these sections at different utility levels. So I put down 1, 2, 3, 4, 5, 6, 7 of them, but there's an infinite number of them. It fills the whole space. So what I like to think about is, if I really drew all of them, it would look like this. There. They're all drawn in white. Right? So all of the indifference curves. In other words, it fills up the whole space. Our first axiom of choice was completeness. And so we are able to make decisions on what we like, what we don't like, over the entire space, all possible combinations. So that's the indifference curve, and we just kind of draw a couple hypothetical ones as we go.
So can two indifference curves cross?
They can't. According to those four axioms, crossing indifference curves would not follow axiom number, was it 4 on transitivity? So A is preferred to B, B is preferred to C, therefore A must be preferred to C. And if you had indifference curves that cross, that would not follow that. Because here we've got A preferred to B, and here we've got C preferred to D, but actually this one is on the same, A is not preferred. So it's that transitivity that gets us this. So these are origin due to one of the axioms on the law of diminishing marginal utility. So that's how that kind of ties in. Now, when we get down, what we're doing today is to say, well, how does the consumer maximize utility? Well, we want to get to the highest level of utility subject to the exogenous factors that we're facing of only a certain amount of income and the price of. So from a two-dimensional space, you can think of trying to push out as far as possible because your utility levels are going up. Again, just making up some numbers here, but maybe this is the utility level of 100, 120, 134, just so we get some different numbers going here, 156. But we know that the numbers are getting bigger in some way, shape, or form according to some function. And so as I move further and further out, I'm getting happier. And so that brings us to our optimal point, is going to be 1 point and 1 point only, where the budget line is just kissing the indifference curve. Because notice on this indifference curve of happiness of 120, if I reallocate my budget, I could move from a point like A to a point like B. And we know that B is preferred to A because it's further out on a higher indifference curve. And you're spending the same amount of money. So having whatever your income is, if your income's $1,000, then I can reallocate my budget by having less beer, more pizza, and I'll be made happier off. More happy. What was the trade-off of happiness called? What was that internal trade-off for a human being? We gave it a name last time or the time before. The trade-off of beer and pizza. I am talking about the marginal rate of substitution. Good. So the marginal rate of substitution is the slope of the indifference curve. And so it changes at each point. At point A, like I have drawn here, and point, I guess I'll call that C. And then if we look at, maybe I'll label this a D. The slope of a curve is the slope of the tangent line at that point. And so people's preferences, their willingness to trade the good, changes as they acquire more of it because of the law of diminishing marginal utility. So as I get more and more pizza, my willingness to give up my scarce beer changes. And so the slope of the indifference curve is the marginal rate of substitution, capturing the person's willingness to trade one good for the other. The budget line tells us the ability to trade one good for the other in the marketplace. The slope of the budget line is equal to the price ratio. And what price goes on top, pizza or beer in this case? The slope is a negative, and then it's the price of something over the price of the other thing. Beer over pizza? So the beer on top? Okay. What was that double check that I said might be a good idea to do? Colby, you're shaking your head?
It's pizza over beer.
It's pizza over beer. That's right. Now that seems weird if you're doing the rise of a run thing. You're like, well, wait a second. Doesn't the rise, isn't that beer? And in this case, it's not. Go back to doing this. What is the price of beer? It's a certain amount of dollars per beer. What is pizza? It's a certain amount of dollars per pizza. Invert. I'm going to skip a step there. So it's pizza over beer. Right? It's the actual quantities being traded off. That's called the relative price, and that's the slope of the budget line when we put it into slope-intercept form. So that's telling you what Target tells you you are able to trade beer and pizza for, according to their pricing structure, according to the price system.
So looking at those indifference curves, those are the typical shape that we've been working with. On the homework, there was a question about what would the indifference curves look like if the two items were like perfectly interchangeable.
Yep. So those are, maybe this is as good a time as any to talk about the extreme cases. So let me pause first. I'll come back to that in a second. Slope of the, as long as I did the slope of the budget constraint here, the slope of the indifference curve, the slope of the indifference curve, the marginal rate of substitution, is the marginal utility of what over the marginal utility of what? We did one problem with that, and that was like our first marginal utility problem. Which one goes on top? The beer or the pizza? Taylor got stung before on this, so who's the horizontal one? Good. So that's one thing that you can kind of memorize in this two-dimensional space. It's always the horizontal axis variable that goes on top. So it's the same thing that happened up here. By the way, this was wrong if you didn't correct it. This was the price of pizza over the price of beer. So this is pizza and beer. And again, if you think about what's a marginal utility, it's a certain amount of satisfaction per pizza. And this is a certain amount of satisfaction per beer. Flip them over and you get your eyes overrun. So the optimal point, the consumer equilibrium, occurs where the slope of the indifference curve is equal to the slope of the budget constraint. And that gives us our first order condition for consumer optimization. So, and I can't remember if your book calls it that or not. That's kind of a technical term. Does that ring a bell? Did you guys talk about first order conditions? I don't think I used that the last time I taught this, but it seemed to just kind of flow out of my mouth, so. No, they didn't use that terminology, at least on a, well, it's optimization condition, but they didn't say first order condition. The optimization condition for consumer equilibrium. So we're going to find the point where the marginal utility of pizza over the marginal utility of beer is equal to the price of pizza over the price of beer. So this is an important one that starts to set the stage for today. So again, this is the slope of the budget constraint. This is the slope of the indifference curve. And if they're not equal, like at point A, the slope of the indifference curve is greater than an absolute value than the slope of the budget line, we've got a problem. And so you'd want to move to point B.
Like a question on the test be just telling the slope of the budget line tells the ability to trade more goods together, and then the slope of the indifference curve tells the willingness to trade.
Possibly, yeah, that's the terminology I like to think of. And that comes from an old saying of having a willing and able buyer. And so what are you willing to do? What are you able to do? Do those things match up? Okay, anything else? All right, so at this point B, with the picture that I have drawn here, that is the optimal quantity of pizza and the optimal quantity of beer that solves the consumer's problem. which we've stated before. So this is the condition that must hold to solve the consumer problem, which is to maximize total utility subject to the budget constraint. Okay. Let's do a couple extreme cases of indifference curves. And these kind of help our thinking too. So Adam, you were bringing up substitutes, it sounded like. Is that right?
Yeah, like perfectly understandable.
All right. So if Coke and Pepsi are, for Adam, perfect substitutes, and currently Adam has 6 cans of Coke, what other point would make Adam equally well off if they're perfect substitutes in consumption for Adam? 6 cans of Pepsi, right? So 6 cans of Pepsi would work. So there's another point. What would be another combination that would make Adam equally well off? 3 and 3, and then anything in between. So at 3 and 3, we're right on a straight line. And so 1 and 5, all of these points represent points of indifference for Adam. Along this indifference curve, utility equals 100 or whatever. I'm just making up a number. So the indifference curves are straight lines. And if we were to draw another one, you know, Adam would be on a higher level of utility with 8 cans. And this would be an 8. This would represent a higher level of utility. So same things going on with getting further away from the origin makes Adam happier. Now, in the optimization process, it's a little different then. What's Adam going to buy, Pepsi or Coke? Whatever one's cheaper. And so it leads to what's called a corner solution in the optimization process. We're not going to have, these are called interior solutions. So point B is an interior solution. It represents a combination of the two goods. But now we're going to be driven to the corner solution. So if Pepsi is twice as expensive as Coke, is the budget line flatter or steeper? So if Pepsi, so if the price of Pepsi equals 2 times the price of Coke, it's steeper. So if Pepsi's 2 times the price of Coke, it's steeper. Okay. Which would mean you'd buy all Pepsi. Something's not right there. What's the slope of the budget line again? So the B line slope is equal to negative price of Pepsi over the price of Coke. So the slope would be, sometimes we need to just put real numbers in. I kind of gave you an equation which was kind of unusual. It just kind of came to mind. I thought it'd be fun since we're having so much fun this morning with equations and stuff. But let's put real dollars in there. If Pepsi's twice as expensive as Coke, so Coke is $5, Pepsi is $10. Okay. So 10 and 5. Slope is 2. So Pepsi being more expensive gives us a slope of 2. This is a slope of 1. So why did we end up getting all of that? Let's take this point just for fun. So I'm just trying to draw a point. Actually, I guess I'm kind of running a risk here, but I guess we'll do this. All right, that's 4. So that's what the budget line would look like. So where would we be made better off if we were here? I know that there's a point here. That's 4 to 4. And so if we're on this indifference curve, could Adam be made happier? Yeah, right? We could go out to this one. Yeah, and so now we're pushing this out as far as we can, which is that point, all Coke. Jesse, you seeing that? Okay. Okay. I saw a little glazed look. I wasn't sure. All right. Maybe it was just from this weekend, following track and all this stuff. We are hitting you hard Monday morning, 9 o'clock with all this stuff. So optimal point is right there. So that's a corner solution. Okay? All right. Extreme case number 2. Let's look at the shoe market. The quantity of left shoes and right shoes of a particular brand. Okay, we'll have an obnoxious case here to start us off. So 1, 2, 3, 4. And 1, 2, 3, 4. So left shoe, right shoe. What's true about these two goods in terms of happiness? Can't have one without the other, right? So we got this 1-to-1 relationship. So if I have one pair of shoes right here, I'm kind of happy. If you give me another left shoe but without a right shoe, I'm no happier. If you give me a third left shoe without giving me any rights, I'm no happier. And same is true down here. If you give me a second right shoe without giving me another left, I'm no happier. A third right shoe without giving a left, I'm no happier. And so the indifference curve looks like this. And maybe that's our indifference curve with 100. How do I get happier? You got to give me them together. So if you give me a second right shoe and a second left, all of a sudden I'm happier. I jump up to 120. So your indifference curves are these right angles. Doesn't have to be 1-to-1. There could be goods that I always have to have 1 bag of chip with 6 beers. Right? So that's my ratio. It's always a 6-to-1. You give me 6 beers, I need 1 bag of pretzels. That's the way I roll. So then you'd have these angles going up, but it would be at a 6-to-1 ratio rather than a 1-to-1. So you'd still have the same look. Okay, questions on that? Now the reason these extreme cases are somewhat absurd, but it does help us with thinking about the shape of the indifference curve for goods that are pretty good substitutes or complements with each other. So as we look at a more normal indifference curve with the slope we're talking about, as we start to get a real curvy one, a real curvy indifference curve means the goods tend to be more complementary to each other. And a real flat indifference curve that's really flattened out, those two goods tend to be more substitutes with each other. So we start to kind of mimic the extreme cases. Okay, other questions there? Another extreme case. What if your indifference curves look like this? Quantity of pizza, quantity of beer. So you go from U10 to U13 to U17. There's 3 indifference curves and they look like that. What is that saying about these preferences? They like pizza, right? So you're a pizza lover, and extra beer does nothing for you. So you're kind of a beer hater, maybe. But you're for sure, the only way you're getting utility increases is by increases in pizza, not beer. So we have a pizza lover. And possibly a beer hater. We don't want to use the word hater anymore. Probably not even. And the way I kind of remembered this, I mean, you can work through the story, but if you want a quick memorization technique, the indifference curves are pointing at the thing you love. So they're kind of like pointing like arrows at the thing you love. Of course, they could be running this way too. By the way, this is going to drive us to a corner solution as well. So whatever budget constraint we put up, if we draw a budget constraint, some old-fashioned way of this, our price ratio and income gives us a budget line like this. How do I make myself happier? I keep allocating my budget to getting this becomes the optimal point, all pizza and beer in the consumer's problem. It's another corner solution. Okay. So that hopefully helps with some of those extreme cases and putting some of the material together. Let's turn to our problem. 4.4. Suppose Antonio gets utility from consuming two goods, burgers and fries. His utility function is given by this, where B is the amount of burgers and he eats, burgers he eats, and F is the servings of fries. Antonio's marginal utility of a burger is that function, and his marginal utility of an order of fries is that function. Antonio's income is 20. The prices of burgers and fries are 5 and 2 respectively. What are Antonio's, I've been saying Anthony all the time, Antonio's utility maximizing quantities of burgers and fries? All right, what's your first step on this approach? What's that? Write a budget constraint, okay, that might be all right. And where from there?
Put the marginal utilities over to.
Good. So start doing this, right? So this is where you're ultimately going to be looking, is towards the budget constraint. I mean, towards the consumer optimization condition. Yep.
The marginal utility for burgers is 0.5b to the negative 0.5 and times f to 0.6.
Yep. 0.5.
0.5 again?
Yeah, that's all 0.5s. got some exponents. So if you need a refresher, remember the square root sign is raising to the half power. That's where that's coming up from. Remember where to go from there? Okay. So with exponents, you can do some subtraction of similar things when they're in fractional form. So if you take x to the cubed power over x squared is equal to x1, 3 minus 2 equals 1. So that's the type of thing you're going to need to do with that one. Handle on the exponents, all right? Remember what to do? So if you've got x cubed over x squared equals x to the 1. So 3 minus 2, we do that subtraction. Remember that rule? So if you've got x to the 4th power over x to the x squared, you can subtract those. That equals x squared. So you go 4 minus 2 equals 2. You got the exponent thing down?
Yeah.
Okay. Okay. On the right track. Anybody get down to an answer yet on the optimal amount of fries and burgers? What'd you get for? You should have, where were you reducing down? You should have quantity of burgers as a function of fries or vice versa. So I think you collapsed too many things down. 2/5 is on the right track, but you've got.
I actually didn't do that at all.
Oh, you did. Okay, so there you need to collapse this down. The thing you got to be careful of. So it's like my x thing, but you've got a half minus a minus half. Okay, so break that down all the way. Okay, so what did you do here on? Alright, so you've got a half minus a minus half equals 1, right? Is that what you're doing over here? And then you've got the halves cancel, and then you've got minus a half equals -1. So you've got, put that back into maybe a fractional form for starters. Yeah, simplify it, collapses it down nice and neatly. So you've got b over f. Let's see what happened to your. Oh, and then set that equal to your price ratio. So that's where you're at this step now. But express your thing that you have f to the -1. Express that as a fraction, and then set that equal. So it looks like most of you are to this stage where if you put those ratios over, you've got that chunk, then set it equal to the price ratio. which the price of beer is what, 5? Is that right? Antonio's income, yeah, burgers, price of burgers is 5, and this is a 2. The dollars cancel, and then you've got your F over B. And you don't have to put the dollars in here, but all this goes away. I got the answers yet? Oh, you did the budget line first? Okay. Oh, you're on that. What's your other one? Are you going on to the next one?
No.
Is that, oh yeah, that is this one, okay. Oh, okay, you haven't done this part yet. I got it, okay.
We'll have to put it back in here. Or is that just given to us for?
Well, let me see where you're at first with the other one. So you've got,
This is kind of up there and then just that.
all right, so this starts to get you down to having one of the quantities as a function of the other, right? So solve this, you're taking the price ratio and setting it equal to the marginal rate of substitution. So your marginal rate of substitution is, and you don't really have it written out right here. Where did your F over B collapse down to?
Where do you have the verb be?
So this garbage here, we got F to the negative half. Let's see, is that right? You got one wrong
No,
here.
that was not negative.
Okay, that's not negative. Okay, so,
So I think I corrected it over there.
okay, 0.5 minus a minus, so the F's on top, right? So that
Mhm.
equals 1. Yeah, so you're right. And minus a minus is to the negative 1, so that's on the bottom. So that's your marginal rate of substitution. This all collapses. The halves cancel. That equals negative 1, that equals 1, that equals F over B.
Okay.
So that's your marginal rate of substitution.
So I did that.
And now
Okay.
the rest of this is you're setting that equal to the price ratio of 5 over 2. So price of beer, so you did it here, so this is it. This it comes so collapsed down that it kind of fools you, all right? So you can now solve for F or B. So solve that equation for F. F equals something.
All right.
And you can forget about those dollar signs too. All right, you look like about the same spot we were at before.
I just don't know.
Where's your F's and B's? How come those went away? What's all this stuff?
That's the top one is the,
Oh, you were putting in the 5 and the 2s. Don't do that. That's not the right, that doesn't belong.
okay,
So starting here, your marginal rate of substitution of burger for fry is equal to the marginal utility of burgers over the marginal utility of fries. And then that equals this. So this cancels. Minus to the 0.5 minus 0.5 equals b to the negative 1. 0.5 minus a minus gives you f to the 1, which is f over b. This now is your marginal rate of substitution. Now you're going to set that equal to the price ratio. So our optimal condition ends up setting F over B to the price of burgers, $5 over the price of fries.
Okay.
That for F. Use that information and solve it for F.
Confused on the collapsing part.
Okay?
When you figure out this, like I understand what you meant by the math, exponents and stuff.
So what I see you guys not doing is following all the way through with showing your equations. So the marginal rate of substitution, let me get rid of this. This is fine. This is marginal utility burgers over the marginal utility fries, which is the marginal rate of substitution, the slope of the indifference curve. So Adam, why don't you squeeze over here if you're kind of in the same spot. So then this is solving for the slope of the indifference curve, that whole thing. The halves cancel. B minus a minus is b to the -1. And then f to the 1, which equals f over b. That is your slope of the indifference curve. Now you're going to set that equal to the price ratio. So f over b in consumer equilibrium equals 5 over 2. And now solve that for f. Solve that system, that condition. That's the consumer condition. Did you guys get to an answer?
It's because it's b to the -1 that the b goes to the...
Yeah, that b goes to the bottom. So yes,
that's
b,
my question.
right, yep. So b to the -1, f to the 1 equals f over b, which is all to the 1s. So that's just a little bit of that. That's where we got to dust the cobwebs off the math a little bit. 5 fries and 2 beers. So Taylor got beer burgers. Yeah. All right. So you've got 5 fries.
Yeah.
So F star equals 5, B star equals 2. Okay. So how'd you get that? That is correct.
I solved for that, and I took the f over b equals 5 over 2, plugged it, we'll solve it for f.
Okay, so if what I left all of you with just moments ago at least was solving this for f. F is equal to 5 halves b. Okay, so that's solving one in form of the for the other. So that kind of gives you that fixed proportion, like my optimal amount of fries is always going to be 2.5 times the amount of burgers I have. All right, so then the next part is where you got to solve for the quantities. We want to have actual numbers here. So Taylor, how'd you pull that out?
I plugged it into the budget constraint.
Into the budget constraint. So she substituted that into the budget constraint. We know that B star lives here and F star lives here. So that's what we're solving for. And so one way to go about it is to substitute that into the budget constraint. So what's our budget constraint? 5b, okay, and let me write this. So I like to think of the income first. So in fact, let me just write it out generically here. So the amount we spend on burgers times the quantity of burgers plus the amount we spend on pizza times the quantity of pizza. 20 equals the price of burgers are $5 plus the price of, I did pizza again, didn't I? This is fries. Okay, price of fries times the quantity of fries. So that's $2 for each fry times the quantity of fries. And now I've got 2 equations and 2 unknowns, right? So there's the budget constraint. Here is our optimal condition, first order condition, or for consumer equilibrium. And now I can substitute this guy of fries equals 5/2 of B into this equation. And so 20 equals, and again, you could manipulate this in different ways, 5B plus 2 times F, but F we know is 5/2 of B, of the quantity of burgers. The 2's cancel. We get 20 equals 5B plus 5B equals 10B, and B equals 2. Now that I know B equals 2, I can go back into this equation and substitute in that B. So that leads to fries equal to 5/2 of B star, which is 2, which gives me 5. And there you go. All right, so there's a lot going on here. Let's try to, why don't you guys write down where we're at and think about what we did. So this turned out to be very instrumental, this consumer optimal condition. Let's call that equation 1. Find that, solve that for, let's call this equation 2. And so that made us able to narrow things down. After doing some work, we had to get this right, get all those exponents right. But at the end of the day, that wasn't too bad. We got down to 2. We knew how to draw the budget constraint. Let's call that equation 3. We substituted, now we're down to that 2 equations, 2 unknowns. So we substitute 2 into equation 3 to yield this result. Let's call it 4, the answer. And now we sub 4 into what was equation 2, back into equation 2. And that gave us our answer.
The very first part, how do you know that the burgers and burgers are on top at first?
You can work it the other direction. This problem didn't give it to us, so good question. Yeah, I just put them that way. Now they did, how did they express the marginal rate? Oh, they didn't give it to us. So yeah, you could, yeah. The other way and the answers will come out. You'll end up getting F over B equals 2/5, and then it'll all shake out the same way.
So, by marginal utility of, what is it, burger, that's what I want to say here.
Yeah, me too.
It would, if it gave that to us in the problem, it would say that burgers was on the vertical or horizontal.
If it gave it to you, whenever it's on top, then it's back to your rise over run thing. If you go utilities per burgers, blah, 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 do all that, then you'll end up having the 2 variables match up with rise over run. So again, this expression here, take utilities per, it's the change in, let me do it a little more formally. So the change in utility from the change in burgers is the marginal utility of burgers over the change in utility from the change in fries equals the change in utility over the change in burgers, invert the denominator, multiply it times the numerator, change in fries over the change in utility, those cancel, rise over run in the graphing space. Is that what you were asking? Like which one goes on the vertical axis, which one goes on the,
Well,
how would you know?
Yeah, I'm saying if that was put into like Word, or put it into the problem to where the marginal utility of burgers was on top, would it say that the marginal or burgers is on the vertical axis or the horizontal axis? Because the way they worded it in the problem at homework, it would say that burgers, imagine that burgers is on the vertical axis.
Okay, then it'll state something like that. And if that's the case, if burgers are on the vertical axis, then you do need to flip that.
Okay, so.
Then it's marginal rate of substitution of fries for burgers.
So that's kind of what I was asking.
Yeah, okay.
It said that, fries was on the vertical axis, then we would.
Yes.
Like that.
Yeah, you need to match. So you have to memorize that that's always on top.
Yeah.
If your memory's failing you, then I like to go back to this to prove out rise over run. Jess?
So where in this question would you figure out that fries is on the vertical and burgers is on, like what's the keyword that's on the?
This particular problem you wouldn't.
So you just guessed and put one on top?
In fact, a graph's not necessary on this problem. So you
But
can.
how would you have known to put marginal utility of burgers over marginal utility of fries?
It might be a good exercise for you guys to go ahead and do it the other way. So if you do the marginal rate of substitution of fries for burger and do this, take these same functions and work it the opposite direction. The one thing you have to do here is flip around your price ratio. If you solve this and go through all the steps, which might be a good idea, you're going to get the same answer. Graphically then, that would be burger on the vertical axis, fries down here. The optimal condition would be still 2 and 5. All we're doing is we're just transferring the numbers around. Okay? But on a problem where, like what you're saying in the homework, where they tell you that this is on the vertical axis, then you have to know which one to put on top. Okay, let's call it a day. So the class